Hello, my name is Adi Swaminathan. I'm a rising senior at Tenafly High School, and today I'll be presenting insights into properties of the moon's surface-forming magma from linear regression on various mineral and compound abundances in lunar craters. I'll now introduce the project. Our initial objective was to examine the mineralogy of the different units that impact craters on the moon, specifically the crater interior and the surrounding ejecta, to understand the differences and similarities between Maria and Highland's composition and variations in mineralogy. We analyzed the following mineral abundances: orthopyroxene, olivine, plagioclase, iron, iron oxide, clinopyroxene, and titanium. Now I'll describe our methodology. We collected the mineral abundance data using the LROC QuickMap platform. We used the line profile tool and captured one diameter extending from the ejecta through the wall and interior and out to the ejecta on the other side per profile. In such a manner, we collected one diameter each from 5 craters of diameter shorter than 5 kilometers and 5 diameters each from 18 craters whose diameters were longer than 10 kilometers to better capture variability around the crater. We then amalgamated all of the separate data from each crater into one table and performed linear regressions between the pairs of mineral abundances using the NumPy, SciPy, Pandas, and Matplotlib Python libraries. So, what did the linear regressions produce? In the correlations between minerals, which were both characteristic of the Maria, many strong positive correlations were observed. In the correlations between minerals, one characteristic of the Maria and the other characteristic of the Highlands, strong negative correlations were observed. However, no strong correlation was observed between two minerals both characteristic of the Highlands. Let us now see why. For each diameter profiled, the LROC QuickMap platform supplied us with 700 equally spaced out data points whose mineral abundances we plotted to perform our regressions. To understand why the correlations we observed occurred, we will perform a conditional analysis. If a data point is from a more basaltic region, we'd expect higher abundances of the Maria minerals and lower abundances of the Highland minerals, and vice versa. This would lead us to expect strong positive correlations where the minerals being compared are both from the Highlands or both from the Maria, and strong negative correlations between one Maria mineral and one Highland mineral. However, we do not observe a strong correlation of any sort between two Highland minerals, contrary to what we would expect. This is because the magma which formed the Highlands was of a non-uniform composition, so merely having more Highlandic material contained in a data point does not translate to having more of the minerals characteristic of the Highlands, while the lava which formed the Maria was of a homogeneous composition, where having more Maria material in a data point does translate to having proportionally more of every comprising mineral. We can test the veracity of this idea mathematically. The total amount of material in the sample should be equal to the amount of Maria material in the sample plus the amount of Highlands material in the sample. If the Maria is of a uniform composition, each basaltic mineral would make up the same proportion of the Maria material in the sample. So, if capital P is that proportion, and Y is the abundance of the basaltic mineral, then P is equal to Y over M. In the non-uniform Highlands, each characteristic mineral would make up a varying proportion denoted by lowercase p of the total Highlands material, and so if X is the abundance of the Highland mineral, then P would equal to lowercase h, X over H. Algebraically rearranging, we are now able to relate X, the abundance of the Highland mineral, to Y, the abundance of the basaltic mineral. Because abundances are measured in weight percentages, the total T would equal 100. So the y-intercepts for the lines of best fit should equal 100 times the proportion of the maria, which is made up by the basaltic mineral in question, or in other words, the abundance of the mineral in the maria. Let us now see whether this condition is met. If we look at this very strong correlation between iron oxide, a basaltic mineral, and plagioclase, a hyaline mineral, we find a y-intercept of around 24. So for the model to be verified, the abundance of iron oxide in the maria should be 24% by weight. Is this value corroborated? Yes, it is. The basalt samples returned by the Chang'e 5 mission contained around 22 to 25 weight% of iron oxide, and as we can see in figure 3, our y-intercept also closely matches the abundance of iron oxide from the 4 Apollo missions which landed in the maria. Similarly, if we look at the strong anticorrelation between clinopyroxene and plagioclase, we notice a y-intercept of 50.508. This value is also corroborated, as clinopyroxene abundances in the maria are generally from 20 to 50%, but abundance can be up to 70% at the center of Oceanus Procellarum. If we take a look again at our equation which models the relationship between the maria mineral abundance and the hyaline mineral abundance, we notice the lowercase p, which was the value for the varying proportion of hyaline material made up by the mineral in question in our expression for the slope of the line. The variation in the lowercase p value explains why the slopes of different clusters of data points from different crater diameters represented by different colors seem to have differing slopes, as can be seen in figure 4. Unfortunately, we were unable to find data for other minerals with strong correlations, but our model equation is greatly corroborated by the observed abundances of iron oxide and clinopyroxene. Furthermore, we had formulated an equation to describe the relationship between the abundances of two maria minerals, also based on the assumption that the maria is of a more homogeneous composition, as opposed to the hyalines' non-uniform composition. Though we are unable to explain it here due to the time limit, this equation was also verified by the observed clinopyroxene and iron oxide abundance data. Thus, the statement upon which we based our models is also verified. The maria have a more homogeneous composition, while the hyalines have a more ununiform composition. But why might this occur? A very plausible explanation for this is that the lava which formed the maria was of a low viscosity, which would allow it to naturally mix, while the magma which formed the hyalines was of a high viscosity, hindering the mixing process, leading to a more non-uniform composition. This idea is actually supported by existing literature. That the maria is less viscous is supported by the book Planetary Science: A Lunar Perspective, which states that the lunar lavas are of low viscosity. That the hyalines are more viscous is supported by a paper published in the Geophysical Research Letters Journal, which states that the moon's crust is formed from a very viscous and stagnant lid. Hence, our mathematical models, as well as our explanations for the correlations we observed, are supported. Thanks for watching, and you can find further correlation results, the mathematical model for the relationship between two maria minerals, and further details on our poster. Thank you for watching.